So last time we were looking at quantiles and selection. So basically the problem which we were looking at. Okay, so we are given a sequence of n numbers a1 to an, an integer k in natural number, and we want to find the rank k element. So for example, median is rank n by 2th element. And we wanted to do this selection in streaming. And there's a lower bound that if you are require one pass, like then you need omega in space to omega in space. So you storing all elements is the best solution. So we were looking at relaxation. One relaxation is like we are happy with coming up with a solution which gives us, let's say, like you're given k and epsilon. So if you ask me for return an element with kth rank, I'm happy if you return me an element which is like whose rank is between k minus epsilon n and k plus epsilon n. And we saw such an algorithm which used a sampling based technique, and it used 1 over epsilon square log 1 over delta samples. And another one was multiple passes and assuming random order arrivals of elements. So we will see. So we started looking at second thing, multiple passes, and we saw why it was used before. And so we saw that if we allow order n space allows one pass, but if we ask ourselves for order one space, then it is possible to do at least randomization. Like in order log n pass with very high probability, we can do quick select. But if I allow myself a p pass, then I can do, if you notice, if I do p passes, then I will take order n to the power 1 by p polylog in space. And for example, for p equal to 2, this is going to take order root n log n space. Okay. But if you notice that if I allow p to be, say, order log n, then this is a deterministic algorithm which basically takes polylog in space. Okay. So in some sense, this is like this could be viewed as a deterministic version of quick select, of the quick select algorithm. Okay. So towards this, we talked about this quantile summary or approximate selection. So what is this problem? So you're given a1 to an, and you're given some parameter epsilon, and you keep a small number of elements from here. And what is the property that you give me any ranked k element, I have in my, say, kernel or core or whatever, an element such that if I return you that, then the property of that element is that the rank of that guy is between k minus epsilon n and k plus epsilon n. So in terms of with respect to this epsilon approximation, if you notice that this is like a small subset or small core. So those people who know core sets, this is like a core sets for this particular problem. Given a1 to an, I'm able to have small subset of my numbers or elements, such that given any rank, I have a number which is within that, which is within one, like k minus epsilon n and k plus epsilon n rank. And we saw that such objects of order 1 over epsilon size exist. And then our question became, how can we achieve, or how can we find this set of objects in streaming, and how much space do we need to do this? And then I told you how, if we can do this efficiently, and by efficiently we mean that if we could do this in order 1 over epsilon log square n, then by some simple trick, we can rederive the algorithm of Munro and Peterson using this approximate summary. Okay. And after that, our whole effort was to come up with this quantile summary, okay, which we could maintain in streaming setting. So then we came up with the following definition of quantile summary. So what is in this quantile summary we would like to do is that we keep small number of elements of my stream. We definitely keep the smallest element and the largest element, some L elements. And for each Q in Qi, we keep an interval. This interval tells us the estimate on the rank of the element which we have stored. Or in other words, in my stream, it gives me estimate on how many elements are smaller than me and how many elements are larger than me. Okay, so with the help of that, I can determine or estimate rank of my element. So this is what the second interval says. This is what this idea of the we keep some points, and for each point we keep an interval, which is an estimate on a rank of this particular element. Okay. So then we saw that one sufficient condition will be that for even given k, if I can find an element in my summary such that the interval of that is contained inside k minus epsilon n, k plus epsilon n, then it definitely implies that if I return this element, then the rank of this element is within k minus epsilon n and k plus 1 n, epsilon n, right? So this was one sufficient condition. And then we asked ourselves, what can we maintain such that this necessary condition is sufficient for us, or this will hold for every integer k? And then we realized that if we can maintain that for any two consecutive integers, if the estimate, or the lower bound estimate of smaller element and the upper bound of the next element is within 2 epsilon n, then it automatically implies that for every element k, there is an interval which is completely contained inside k minus epsilon n and k plus epsilon n. And we saw that if this wouldn't hold, then this invariant will be violated. So far so good. And then this was the property of our summary, that we would like to maintain this invariant property in streaming. So if we can come up with a set of intervals, set of points and set of intervals which satisfy this invariant property, then at the end, because of the property, because of the characteristic which we can derive from this invariant, we can say that indeed our summary is good, or it's an epsilon approximate summary for us. And to do this, we said, okay, we are going to apply this idea of merge and reduce prune framework. So what is the meaning of merge? So you are given, say, think of this, that you're given here is one summary, and here is one set of stream, and this is next stream. And here you are given some epsilon 1 approximate this thing, and this is an epsilon 2 approximate. And with the help of this, we would like to get a merge and get a summary for the combined data, or combined database, or combined thing. And we said, okay, how can we merge these two summaries? And then we gave a method to merge these two summaries, which is basically you just take the union of the summaries of these two together, sort them out, and then appropriately we found intervals. Like we said, okay, fine. So basically to find these intervals, we said, looked at this element, what estimate does I have in the first stream? What estimate can I get it on this in the second stream? We took the sum, and that was the estimate we took for the intervals. And this is exactly what was happening here. Okay, so that gave us an estimate, and I did not prove it because it was a very case analysis, that indeed this is an epsilon approximate quantile summary for S1, S2, where epsilon is max of epsilon 1 comma epsilon 2. Okay, but notice that this is one key property of merging, is that merging keeps accuracy but increases summary size, because all we did is we took the union of them, or rather, like multi-set union of these objects. Okay, now, so we need a lemma which, so the way our algorithm in streaming is going to do is like we are going to fix a threshold, and the moment we see some amount of elements in the stream, we'll keep a sketch of this or the summary of this. We will, for another set of points, we'll keep a summary. And now, before the another data comes, we'll take the union of these two summary to get the summary of the whatever I have seen so far. But now the size has become too big, so I need to prune it so that the size becomes smaller. Okay, so like it will become clear when I will explain how will we implement this in the streaming, the importance of merging the summaries and importance of pruning the summary. Okay, so then we went on to pruning this summary. So what was the pruning this summary? So suppose you're given an epsilon approximate quantile Q, and an integer h greater than or equal to 3, then we can find a q prime. So the size of q prime is h plus 1, and q prime is epsilon approximate summary, where epsilon prime is epsilon comma 1 plus 2h. Okay. Okay. So now, how did we achieve this? So then we said, well, okay, fine. So basically, now I only have a space of h plus 1. Then ideally, if I knew that to whole data set, then I would have probably kept the n by h ranked element, 2n by h ranked element, so on and so forth. So now I don't have that, but all I have is this quantile. So now let me ask this this summary. Let me ask this summary to return me an element which is close approximate to n by h ranked element, 2n by s ranked element, and so on and so forth. So this is what we did. So if q1 to ql, we assume that l is greater than or equal to h plus 1, otherwise you just keep the same thing. And we query q for the ranks 1 by 1, n over h, 2n over h, 3n over h, and nth, and we created q prime from these queries. Okay. And what are we going to do as in intervals? We are going to use same intervals as those in Q. Okay. So this is what we learned last time. So if you have any questions so far, please let me know. I have not yet proved why this Q prime has a property, but is the algorithm to construct this object clear? Okay. So now notice what I need to show. So I have so that this is an epsilon approximate summary, what do I need to show? I need to show that if I take two consecutive points, okay, and so for say suppose this is some qi and this is some, let's not call it like, okay, the q we are calling it. So let's call it qi prime and qi prime. Okay, so these are the two objects. Now I would like to say that look at the interval of iqi prime and interval of qi plus prime. Their difference is not too much. And why that happens? Well, look at this. Look at this picture. So basically, so these are the intervals, say with respect to q. So this is say with respect to q. And what did you choose? You might have chosen this one and maybe chosen this one. These are the two consecutive. This corresponds to say I minus 1 n. So, or let's say, I mean, doesn't matter. In by h, and say this corresponds to I plus 1 over n by h. Okay. So what is the difference between these two? Well, the difference between these two is, notice, is basically the difference between these two is going to be I over h, right? Because these are multiple of this. But there are two things that we have to keep track of. Now, this number is within some epsilon n of this. This number is within epsilon n of this, right? So the difference between this point and this point, okay, say this point is b and this point is a, b minus a is basically at most ih plus 2 times epsilon n. Okay. No, why I wrote I? This is not I. It is 1 over h. Okay. Now, what is this? If I take 2 common, then what am I going to get? Epsilon plus 1 by 2h times n. But this is exactly what my epsilon prime is, right? So I have shown that the two consecutive guys are difference is 2 times epsilon prime by n, which implies that what we have been, this is exactly what we wanted to prove, right? That this is an epsilon approximate summary for epsilon prime being epsilon plus 1 over 2h, right? And precisely, we have been able to show this. Okay, so this ends the construction of merge as well as reduce. Okay. Okay. So now, what I need to show to you, how am I going to use them to achieve. Okay, how do we? So now the next question we will say, okay, how to maintain summary. Okay, how to maintain. So this is today. What is the date? December. How to maintain epsilon approximate summary in streaming. Okay. So we'll worry about it. Yes. So what we are going to give is an order 1 over epsilon square log n, log square n space algorithm based on reduce and merge. Okay, so this is a way. So first, let's come up with a solution as if the whole stream is available offline. Okay, and secondly, then we'll show how we can implement this in small space, in fact, same space. In streaming. Okay. Okay. So basic thing to know is that I think of this as like a, we will think of this. So I know n, number of elements, because currently we are in offline setting. Okay. Otherwise we have to do something else. Okay, we'll worry about this later. But now in offline setting, I know. We will pretend, we will think of our data as, let's say, as binary tree. Okay. So what I mean by this is that, let's say, we have A1, A2, A3, A4, A5, A6, dot, 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 AN, and here we have AR, say, or the root. Let's not, this is not AR, this is root. Okay, so what are we going to do? So now look, data is given. So think of this as an array, but the extra space which you are allowed to use is very small. So how we are going to implement this? Well, I read first two, okay, and whatever it is, okay, and I'm going to compute some summary here, say Q12. And then I look at this. So I look at the first two elements, so in the bottom up, each guy is a summary in itself. And whenever you look at the root, any node in the tree, this is going to contain summary of all the elements that you have seen, like that is under the subtree rooted at this vertex. Okay, so that is the protocol we are going to maintain. So for example, so next, A1, A2, A3, A4. So suppose this is going to contain Q3, 4, Q5, Q6, so on and so forth. And here it is going to contain Q1, 2, 3, 4, so on and so forth. Okay. Now, how are we going to implement this? So first we will see A1, A2. We have a summary Q1, 2. And then we'll keep aside this summary. And then I see, oh, more numbers are coming. Then I see A3, A4. Great. I compute Q3, 4. Okay. The moment I get Q3, 4, so at any point of time, we will maintain the following invariant. At any point in any level, only one summary is presented. Okay. So this is something which we'll maintain. Okay. This is some invariant which we'll maintain. And why this is so? Because the moment I see Q3, 4 has been produced, okay, and before any element come, what will I do? I will take Q1, 2, Q3, 4, and this is merge of this. And the moment I get Q1, 2, 3, 4, okay, so I'm ready, right? So now, when will I merge this? When I will get, say here, Q 5, 6, 7, 8. And at that point of time, notice 5, 6 has come, I'm waiting. The moment Q7, 8 is made, I take this and merge it and move forward. And the moment Q5, 6, 7, 8 will come up, now Q1, 2, 3, 4 is ready with this. So the moment the second object has come in this, we will take this, merge it and move, merge and move here, Q1, 2, 3, 5, 6, 7, 8. So on and so forth. This is how we will implement this. Okay. Now notice, so what happens? So when I merge this, as you have noticed, merge maintains accuracy, but increases size. Right? Increases size. Okay. So the moment I have merged, what will I do now? I will call here reduce. Merge. Like, so the moment you do merge, then you will apply the operation reduce on that object. Okay. So is the goal clear? Is the algorithm clear? Look, I haven't told you that what will be meant, like how will we achieve the space bound and everything, but is the goal clear? Okay. So to prove, so the algorithm is, this is what we will do for the algorithm, which is basically the moment the data are available to me, I get, like the moment I have a summary, I take the merge of these two summary. I know my summary is big. I apply my reduce operation. So to do this, I'm going to fix some h. Fix some integer h. Okay. And what is the invariant? For every summary is of size h. Okay. Or size h plus 1. So now tell me how much total space this algorithm is going to take. Additional space, how much? So if we agree that at any point of time we have at most one summary at any level, right? Then it is going to be, how many levels are there? It's a binary tree. So log n and into h plus 1. Okay. So this is what my summaries, this is what the total space is going to be. Now let's ask what about accuracy? What about accuracy? Well, here in the bottom, every everyone is like very accurate, like it is 1 accurate. But as we go up, accuracy decreases by 1/2h. So what does it implies? So it implies that epsilon of root is going to be epsilon of leaves plus, say, depth times 1/2h, right? Now epsilon is fixed in the beginning itself, right? So what I want my epsilon root to be less than equal to epsilon. Now, so that tells me that what h should be, like what h I will call that my accuracy will be, right? Epsilon of leaves is, say, 0, right? So it implies that d/2h should be less than equal to epsilon, which implies that h has to be greater than equal to d/epsilon, which is like order log n over epsilon. Okay, which implies, so then what is your total space then? So if I fix h equal to order log n over epsilon, then I know my accuracy is going to be epsilon as was designed by, asked by the algorithm. But now, what is space? A space was like order log n times h plus 1, which is ordered 1/epsilon log square n. Okay? Right? Is this clear? Okay. So notice that we could maintain this in, why am I? Okay. We could maintain this in streaming also, except one problem. We don't know h. Okay, we don't know h. What can we do? Or we don't know n actually, right? And if we don't know n, we don't know h. So what can we do? Have you seen this trick to handle unknown n?
Some sort of a doubling trick? Guess something?
Yes. Yeah, so you're right. We need to apply some sort of doubling trick. Okay. So I don't know if anybody has seen it before. So let's do it, because this is a general trick which is applied even in online algorithm and all this where we do not know unknown n. So as Venkatesh was saying, so this is like, let's say, let's call this handling unknown n. Okay. So first, let's do this doubling trick. So you fix some n0, say n0 equal to 1000. Okay. Now you start with this constant n0, some constant, doesn't matter. And you make tree with n0. You know now n0, but you also know epsilon, right? So this is good. But the moment you become more than n0, what will you do? Well, now you double. So, but now you have an epsilon summary of first n0 elements. Okay. Now, look, I mean, because my n0 has increased, it's not that I should just restart all over again, because that could lead to a lot of issues. Okay. So what you do, you don't restart. You start from here, and now with a new estimate that it is 2n0. Okay. And next time, if it happens, you make it, if more number comes, you increase it to more 4 and 0, so on and so forth. Okay? Now, finally, you will get some number, get some 2 power k such that 2 power k n 0, 2 power k n 0, such that it is almost close to the real n. Okay? Now, look, so I have kept all this tree for several reasons. Now, how are we going to answer queries, right? How are we going to answer these questions? Like if a query comes, what will we do? Like if I give you a number k, where will you go and search and give me, okay, take this, right? So notice that this is, for example, this is with respect to some data, right? A1. Next set of data, A2. Next set of data, say A3, and last set of data, AK, right? So this is how, this is summary, epsilon summary for data of A1, epsilon summary of data in A2, so on and so forth. Oh my God, there is something wrong happening with my machine. I could be in soup soon, so let me. Okay, but this is where we will use this idea that merge do not reduce accuracy, right? So you just merge them all together and then use that. So you do merge of A1, A2, dot, 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 AK, and use that data structure. And size will be just the union of all this, but accuracy is great, right? Accuracy is going to be epsilon. So you are very good with respect to this. But now, how much size did we take? Look at the size bound. My size bound is going to be, let's see, first one is going to be 1 over epsilon log square n0, 1 by epsilon log square 2n0, so on and so forth, 1 over epsilon log square 2k n0, which is like n, right? So notice there's something not desirable happening here. Why? Because this itself is actually 1 over log square n, right? And how many such terms are there? So there is a like roughly log n term. So this is like roughly equal to 1 over epsilon log cube n, right? But this is not what we wanted. We wanted to have at like just log square n. But when we did this doubling trick, unfortunately, what happens is, at least in this setting, that the space requirement, like space goes beyond a log square, which is not bad. But there is some simple trick which you can apply here, and that can reduce a space. So to reduce space, what we are going to do, we are going to do what is called squaring trick. Okay. So rather than when you got n0, and when the number next time comes, you do n0 square. Okay. Then you go n04, so on and so forth. Okay. So now what is happening that you are going at, you are making your trees at much larger speed. So it's basically 2 power I. So in the ith time, you're going to do 2 power. And the reason is because we are in the logarithmic space regime. So we can go much faster than this linear rate which we achieved in the last trick. Okay. Now, if you do this, what we can show, I'm not going to do this computation, like it's a good exercise to do this. If you grow at this rate, then we can show that we only lose some constant factor, which is like 1 over epsilon log square n. Okay. So with this squaring trick, we can achieve the desired. So with offline and online, we didn't lose much. So for example, so because we were in the logarithmic regime, we can do a square, and like, so if you're in log n, then you should do you should grow even more faster pace to increase your space tricks. Okay. So this is all that I wanted to tell with respect to this algorithm for quantiles. And what I did not tell, okay, so let me just at least write it down. So if you do 1 over epsilon log n0, 1 over epsilon log n0 whole square, so on and so forth, then this is actually equal to 1 over epsilon log square. Okay. Okay. So so far so good. So the things which I did not teach. So let me at least tell what I did not teach here, and I'll cover here. Okay. So what I did not cover here is this random order arrival. Okay. So there are several ways of doing this random order arrival. Okay. But the one which has been studied in this setting is, let me tell you what is studied in this setting is the following. So we select A1, A2, AN adversely. Okay. However, we assume that elements arrive in the order given by a uniformly random chosen permutation of A1 to A. Okay, so these numbers are A1 to N, but think that these are like now you have you take a random permutation of A1 to N, and this is how the data is coming in the stream. In this model, what already Munro Peterson in 80 showed the following, that median requires order root log n space by a one pass algorithm. Okay. Okay. So if you assume that the numbers are coming in this model, then in one pass algorithm for median requires order root n log n space. Okay. With high, of course, this is with high probability. And this with high probability is with respect to randomly chosen permutation. Okay. So this is something which I didn't teach, and it's an interesting algorithm in itself. And then later, okay, so this also has some this also will imply that order log n pass is good enough for constant space or polylog n space. And later, Guha and McGregor showed that they got the most optimum thing, that in fact order log n passes suffice with order log n, like for polylog n space with high probability, right? So Munro Peterson showed that actually median or any of this, like if you take one pass, I can do it in order root n log n space. But if you allow just polylog n space, then they still took order log n passes. But later Guha and McGregor, I think quite like 2013, 14 or some point of time, they showed that in fact log n passes suffice if you are actually in this model, if you are interested in polylog n space. And they also showed that this is a lower one, like in the sense that if you really want to achieve polylog n space, then you do need order log n space, like modulo some divided by some polylog n space, like polylog n in pass, like much smaller than log n. Okay, so this is all that I wanted to tell about with respect to quantiles. Now let me give you a small set of things which I actually did not do at all, which I wanted to do, and probably I will offer to some kids who wants to do it. Just do these part some point of time next semester. But let me tell what one or few things I did not do, which is an integral part of this course. Okay. So first thing which I did not do is something called let's say things we didn't do. Okay, so first is called distributional Johnson Lindenstrauss lemma. Lindenstrauss lemma or DGL lemma. Okay, so what does this tells us? Okay, so this lemma statement is you fix vector x in R to the power d and let pi be and a matrix, a k cross d matrix, where each entry pi ij is chosen, say, uniformly, okay, in quotes, okay, from -1, 1, okay. Then if k, it's say roughly omega 1 over epsilon square log 1 over delta, then with probability at least 1 minus delta 1 by root k second norm. So basically it says that it preserves distance. Okay, so what does it tells us? It tells us that if you take, say, z equal to 1 by root k pi x, okay, so this is a projection of x from d dimension to k dimension, okay, where k is like roughly 1 over epsilon square log 1 over delta, okay, dimension, while preserving distance or length, whatever you want to call length, to within 1 plus minus epsilon factor, right? So this is basically, so I give you a vector x, then you can choose a matrix, like random matrix, in fact, where the entries are from 1 minus 1. And what property does it has? Well, the property it has that if you look at this vector z, which is 1 by root k pi x, then we can think of this that we have taken a long vector, we have projected to a small dimension without affecting too much in terms of distance. Okay, so this is the key lemma about distance preserving or like by reducing the dimension. Okay, and what does, so a matrix form or metric form of this is called Johnson JL lemma or Johnson-Lindstrom lemma. So what is Johnson-Lindstrom lemma? So this is a JL lemma. Okay, so what is JL lemma says? Okay, so this is like, or this is like, it is also called metric Johnson-Lindstrom lemma, is that now let V1, V2, Vd, Vn be any n points, vectors in, say, in Rd, then for any epsilon in 0, half, what is the property? There is a linear map, which basically means there's a matrix. There's a linear map f from Rd to Rk, where k is like roughly 8 ln n over epsilon square, okay, such that for any I j less than equal to n, what we have, so the distance between or the length between any two vector is preserved. Right? So what this means that, look, I can come up with a, like, so basically, and moreover, f can be obtained in randomized polynomial time. Okay, so basically f is given by simply a random matrix pi. Okay, so basically notice the distribution J lemma. I wanted to preserve the distance of just one vector, right? So I had this k cross d matrix. Okay, now I have n points in Rd and I want to preserve distance between every pairwise distance. Okay, so now rather than taking, so I just think of this with that for each one of them, like I have this 1 over epsilon square log 1 over delta, and if I take the matrix slightly fatter or thicker by roughly like 8 ln n over epsilon square, so I choose this matrix slightly thicker, and then I'm saying that, look, now it preserves the distance of everybody else. And how do you derive so proof, once you have the distributional JL lemma, proof for this is fairly simple. You basically apply distributional JL lemma with delta equal to 1 over n squared and union bound over n choose 2 vectors vi minus vj. Okay, that's it. So I'm not going to give you a formal proof, but you just apply the distributional JL lemma with delta equal to 1 over n square. Then what will you achieve? Then automatically you will get 1 over epsilon square log n factor will come here, right? So that is how you will get. Now you want to say that, look, for one particular vector this happens, so you apply this with respect to vi vj. So what is vi vj is like one particular vector. So if I apply this particular lemma with this particular so what I'm going to achieve? I'm going to achieve that, well, for one particular vector, I'm going to achieve that the distance is within, how much it will be, like 1 over at least 1 minus delta. So the failure probability is at most delta, which is 1 over n squared, right? And so, or you can apply with this 1 over n cube or something, right? So you want to achieve that the distance between them is not too far away for all n choose 2 vectors, and this is why you can do over union bound, and this will still be good. Okay, so this is something which I did not tell. Okay, and so the technique. Yes, Feder.
But this linear mapping is the same matrix pi, right, or not?
Yes, it's the same matrix pi, Feder.
But what does it mean that it can be computed in randomized polynomial time? Because basically you say it's a matrix, every entry is a uniformly -1 or +1.
Yes, Feder. Yeah, so this is exactly
constant running time, actually.
No, Feder, because you have to fill in the whole of this matrix, right?
But you know what you know every entry, right? Or
yeah, you know every entry. This is true. Right? So, I mean, in that sense, yes. In that sense, yes. Yeah, so you can give a succinct definition of pi. This is true. Okay? So all I want you to tell that, so this distributional JL lemma is the key lemma of all the dimension reduction tricks. Okay? And so this is like what it tells that for one particular vector, if I wish to, and this is not how Johnson-Linderstor proved, it is the later proof by Eclopiotis. Okay, I cannot pronounce his name. The person who does this random things, Eclopiotis. Okay. So he
Optas.
Yes, correct. So he proved this for its application in databases. Okay, and so there are lots of interesting versions of this. Now that we have read so much about all these things, I think proving this is it requires a bit of technicality. Maybe it would have taken me one lecture, but not more than that. Okay. But then we can prove lots and lots of interesting properties starting from this. So even if we don't know the proof of this particular lemma, there are lots and lots of proof which uses this with appropriately chosen parameter of delta. Okay, so this is something which we should keep in our head when we try to make any algorithm, and what it does, it preserves distance. Okay. So now I want to say slightly even more stronger version of Johnson-Linderstor lemma, which is the another key object which is used quite a lot. Okay, so let me tell you what I mean by this. So this is called subspace embedding. Okay, so suppose we have a linear subspace E of Rd of dimension L. Okay. So now the question is, can we find a projection pi from RD, okay, or to say some RK, okay, what is the property? Such that for all x in E, pi x, like the distance with respect to pi is preserved. Okay, is 1 plus minus epsilon, right? So what is the difference between the previous version and this version? Okay, look, previous version, you give me V1 to Vn, n point or vectors in Rd, and you want me to find a projection which preserves the pairwise distance. Am I right? Okay. Now, what does this tell us? What does this want? This wants this. Look at this, is E is a subspace of R to the power D of some dimension L. I want to find a projection matrix from R to the power D to R to the power K such that it preserves the norm of each vector. Or in other words, if you would like, also you can say it preserves pairwise distance for every pair of vertices. Okay? But let's not go there. But for now, I want to, yes?
But here, dimension of E is not important for you.
It is important, L.
Ah, okay.
So you might ask, what is the value of K? Yeah. So now two questions you can ask. First question, and this I will leave you with. Can K be less than L? Can we have a projection matrix where the R to the power K could be strictly less than L? Is it possible at all? Okay. Okay. So it's a good question to try. Okay. Think. And can we have K equal to L? Right? I mean, first of all, these objects should even exist. Look, you can't. Okay. So for K equal to L, actually it exists. You basically take E, take orthonormal basis of E, right? So if you take an orthonormal basis of E, that is also mapping from here to basically, this is just going to give you elements in E itself. So of course, this property is going to be satisfied, right? But there's a problem. So as an algorithmically, there's a problem because problem is we need to know E, right? Then I can find this orthonormal basis, okay? So this is why there's a word called oblivious subspace embedding, means I do not know E and I still have to come up with this mapping pi from R to the power D to some good like dimension, right? Of course, this dimension has to be greater than or equal to L. So it will depend on that and maybe slightly more such that that I can preserve the distance or the length of each vector in E without knowing this E. Okay? You get the question or you get the value of the question. If I knew E, then I can actually find a basis of orthonormal. You can find a basis and turn into an orthonormal basis, and you can show that that is the right projection matrix from R to the power D to R power K, which preserves the distance as desired. Okay? But I do not have an access to E. Like the way most applications in big data is used, you have no access to U, but all you know is that my objects rely in this subspace of this particular dimension. That's it. Okay. So here's a theorem which is proved, and again using a very non-trivial application of distributional. So this is called Oblivious subspace embedding. Okay, so suppose E is a linear subspace of dimension D. Let pi be a distributional Johnson-Lindsay lemma matrix. Okay, pi with pi being an element of R, say K cross what should be, just 1 second, it should be, let me see. Okay, I do not want to mess up, so let me just let me look at the right quantity. Okay. Subspace. Okay. So E is a linear subspace of dimension D, subspace of Rn of dimension D. Okay, and so this is K. So this is like K cross N matrix. Okay, with K being equal to big O of D epsilon square log 1 over delta. Okay, then with probability 1 minus delta for every x in E, what is the property? Is that if you look at their projection vector 1 by root k pi x, right? Second node or the distance is, okay. So basically it takes that if you take a random matrix with of dimension d over epsilon square log 1 over delta, okay, then that matrix is good for for your subspace of dimension d which you had in your head. Okay. So is the statement clear? Right? So it is basically, look at the distributional Johnson-Lindsay lemma, right? So if I wanted with respect to one vector, then I have to choose a matrix from this. If I wanted for n particular vector, then I apply this with delta equal to something, right? But now I'm talking about subspace, and the problem with subspace is that it has infinitely many vectors, right? So I cannot do anything as such, but even then this lemma tells us that I know that E has infinitely many vectors, but even then I can come up with a matrix pi, okay, which is in distributional JL lemma. But now you take the number of rows you take in your matrix is some d over epsilon square log 1 over delta, then I can guarantee that for every vector in E, the length is preserved up to the factor of 1 plus minus epsilon. Okay? Okay. So again, the proof is quite non-trivial, but the idea of the proof is quite beautiful. So this is what is used. I don't know whether you have heard of this. This is called net argument. So basically, what you do that you cover the whole space with, we choose a large but finite set of vectors. Okay, okay, vectors T carefully, and this is what is called net. And what you show now, you apply, prove that pi preserves lengths of vectors in T, again via union bound. Okay, and now what you say, argue that any vector x in E is sufficiently close to a vector in T, and hence pi preserves lengths of x. Okay, so basically, this is a very famous net argument which is used, and these are recent developments with respect to what do you call JA lemma with applications. So you choose very large but finite set of vectors T. Okay, and basically now you apply your JA lemma with respect to T, and you know that all of these preserve distance because this is how you choose your the precision parameter delta. Okay, and now you say that okay, fine, with respect to these points, I'm very good. But like these are like now you say that look at any point is close, like is very close, like is within some small ball inside this. So if now you apply triangle inequality to say that look, the distance of this cannot be too far because then the points which I have chosen in T will have large distance of something of this nature. And this is how you argue that the subspace embedding is good. But algorithmically, this is all about distributional JL lemma. There's nothing more. And where does this find application? This has amazing amount of, at least this has lots and lots of applications. Okay, so this has applications in matrix multiplication, regression, SVD, and so on and so forth. So basically, what we want. So what the basic idea is that you want to perform some operations on matrix A with, say, n data columns. Okay. Say in large dimension RH with small effective rank T. Okay. So basically, we want to reduce the size of matrix roughly to R D cross D by spending time proportional to NNZ of A. You know what is NNZ of A? This is number of non-zero entries in A. Okay, so in these applications, we apply this subspace embedding. Okay, but I mean, yeah. So this is so my idea. The one aspect of my course which I did not cover is this aspects, which would have taken me 3-4 more lectures, like applications as well as these things. And one more further aspect apart from these things which I wanted to cover and which I did not cover, and again that would have taken 1 or 2 more lectures, is core sets. Okay, so core set at least I didn't prepare, but this I had prepared some point of time. So the core sets, this is a topic that comes from computational geometry. Okay, and let me. So what I wanted to cover, there are lots of topic in this area, and it's a very hard choice to choose in what one can cover. Okay, so what happens in code sets is like you're given some point P, a collection of endpoints in RD, and what we want to compute some function f of p, for example, K clusters P according to some objective like K means, K median, K center, etc. Okay, and also find a smallest ball that encloses P. Okay. So what is core sets? So core sets is basically Q such that cardinality of Q is small and the function that you want to compute on Q is similar to the function which you want to compute on P. Of course, it depends on the function f, and secondly, ideally, Q should be computable quickly. Originally, the way it was, originally, Q was subset of P or a weighted subset, and hence the name core set. Okay, but now, like the way we have our compression and kernel, people now actually come up with a core set which may not be a subset of this, but computing things are equivalent. Okay, so for example, let me tell you, one example which so this is like minimum enclosing ball. Okay, so what is minimum enclosing ball? So you're given endpoints P in RD, find smallest radius ball BXR such that P is contained inside ball around this. Okay. So for this, there's a theorem quite a interesting and cool theorem which says the following: for any P in RD, there is a set Q subset of P such that cardinality of Q is at most 2 over epsilon and minimum enclosing ball of Q is 1 over 1 plus epsilon approximate to minimum enclosing ball of P. So now notice Q is an epsilon core set of P, and more importantly, no dependence on N or D. Okay, so this is with respect to minimum enclosing ball. So there are some classical computation of this, but in recent time, people have studied how to implement this in distributed setting, how to implement this in streaming setting, and that requires going beyond what was known or what follows from the computational geometry perspective. Okay, so if you have seen the book of Serial Hall-Pellet, he has a chapter on these topics, but even like Fox talk lately, people have been studying these things, and because in different settings, you need to construct different things. Sometimes there is a dependence on dimension based on the objective function. Can we get rid of this dimension? Can we prove some lower bound? So on and so forth. Okay. So there are also code sets for clustering. So for example, for for K median and K means, and then you have what metric are we talking about? Okay, so there is a general metric space. There is order poly K log n 1 over epsilon for an epsilon approximate code set. Then there are there are also for some poly K comma 1 over epsilon, which is independent of dimension. It was proved by Feldman, Simard, and Zoller in 13, and then later by Zoller and Woodruff. And there was also a recent paper by Markechev and Rajasthan, who reduced the dimension of these points to order K log K over epsilon square and things of this nature. So this is a fertile area. And so this is one topic which I definitely wanted to cover, but too much time. Okay. Anyway, so this is all. So I will, so I do plan to teach all these things, but like more in a relaxed fashion than a course, sometimes in middle of January. So I will send you an email if you wish to, but I'm going to only cover the materials which I did not cover this semester. So I'm not teaching any courses per se, but I'm going to teach these aspects of big data, which I didn't have time to cover, so that I have lectures recorded for these things for future purposes. Okay, so this is all that I wanted to tell today. And yeah, so, and I did not tell the techniques or the tools which are used, like things like importance sampling but the good thing about most of these things in streaming is that you come up with these two tools of merge and reduce and do things as we did for quantiles. In my opinion, quantiles is a easier example to give this interesting idea of merge and reduce. I mean, this is like if the way we do, if, for example, everything with representative sets also is exactly like this. We merge, take the union, and that is merge, and then we reduce, applying the reduce operation. So, okay, so that's all that I want to tell. And I think I've sent out the exercise also for people who are taking the credit. So formally, I'm done with the course until you have a question.
Saket, can we come back to this net arguments?
Okay, this one?
Yes. So, for example, if I want to embed a plane into a line, right?
Plane into a line.
So plane is infinite, right? So how I would, and I have infinite, uncountable actually number of points there. So yes. How I approximate this with a finite set of vectors?
That's a good question. So based on this epsilon, okay, I will choose some set of points, okay. Like it requires hard work, but when I say finite, it depends on the dimension of E, okay. So and epsilon. So the number of points which I'm going to choose depends both on the subspace, which I like the dimension of the subspace which I wish to embed, as well as the accuracy parameter which you have given to me with respect to the path. So it depends on both things, and it actually exponentially depends on these things. So they are not polynomial dependence on this. You want exact bound? I can tell you exact bound. Just give me a minute.
Or if you can give a pointer to where I can find it.
Yes, I can send you the lecture notes.
Please,
yeah. Okay, just let me see what it says. I have lecture note for this, so I can send you this. So the size of this is e power big O of d, Federer. Okay. Yeah. So this is like e power big O of d. Yeah. So you basically you make some small grid, and from those grids you choose appropriate number. Like so, you make a grid with size length epsilon over d. Okay. So you make grid of size, length, epsilon over d. So I have taken all these things and I've taken this grid of size. So now number of grid vertices is going to be roughly 2d by epsilon to the power d. Okay, and then so this is like some sort of weaker net. So you take these points of these grids as your t. Okay, but this will give you like 1 over epsilon square d log d over epsilon dimension, and you can do slightly more careful net argument to give a tight bound. But basically what you do is like you put it, you make it in a grid with sufficiently many small points, and you take those points as this, because now what happens that if your point lies within those grid cell, then you know that it is closer to one of these guys. So this is how it is done actually. Okay, but I'll send you the link.
Thank you.
Saket, I have a question about JL lemma. So
please tell me.
So you have stated this with respect to L2 distances. So do you know for other for other P and with LP distances, what kind of dimension reduction can we obtain?
There was something I read, but I do not recollect completely. But this I can check back and let you know. Okay, I can check back in my notes. I did see something of this nature, at least as a matter of like it is not as good as this, but there was something which was known. Okay. So or a proof that you cannot do something of this nature is known.
Okay. Yes. Thanks.
So, for example, there's a lot of work by Elon that is this. Look at the dimension 1 over epsilon square. So, like this 8 ln n over epsilon square. So, call it order ln n over epsilon square. Can you do asymptotically better than this? So, actually, Elon came up with points, n points, very carefully chosen points, and then he showed that look, if you want to preserve this distance, you cannot do less than this dimension. So these kind of lower bounds are known, but what happens is that generally this matrix is very dense. Okay, this matrix pi is very dense because so applying this matrix pi is a very expensive operation. So people have come up with a efficient, sparser version of Johnson-Lindstrom lemma with a matrix pi which has a small number of zeros. So this kind of work has happened quite a lot, but with respect to different norms, I haven't seen much. But I have seen 1 or 2 pointers. So I will look at it and then let you know.
Okay, yeah, thanks.
Okay, good. Then if there are no questions, so when I do plan to take lectures on this, I will, at least the people who showed up today, I'll definitely send an email to them. Okay? Okay. Good.
Okay, thank you for the lectures.
Thanks a lot.
Thank you, Saket.
Thanks a lot.
Thank you.
Yes, okay, great job. Thanks a lot. You entertain us for the half of the year. That was very nice. Thanks a lot.
Thank you so much, Saket.
Thank you.